Good afternoon, everyone. It's great to see so many people here. Welcome to what we hope will be the first in a series of briefings that will be held over the course of this year on high-impact science. That is science research that's going on out in the community that has a huge impact on our lives, our culture, our economy. Today's meeting is made possible thanks to the generous support of a number of individuals, in particular, Congressman Lamar Smith, Congressman Jared Huffman, the House Science Committee, and the University Corporation for Atmospheric Research. My name is Tom Bogdan, and I'm the president of the University Corporation for Atmospheric Research. We are a very unique organization. We are a not-for-profit coalition of 105 of the leading universities from across the U.S. and Canada that carry out research and education in the areas of weather, water impacts, climate, air quality, and yes, even space weather, which is a form of weather that really has its biggest impacts on our advanced technological systems as opposed to more traditional weather impacts. Since 1960, our organization has had the honor and privilege of operating the National Center for Atmospheric Research. The National Center is the oldest and largest federally funded research and development center of the National Science Foundation. It has offices and installations in Colorado, Wyoming, Hawaii, and Washington, D.C. Today's lecture is about El Niño. And El Niño, as you'll discover, is above average surface sea temperatures that show up periodically from time to time, but not as periodically as we would like, and that's going to be the course of our discussion here, in the central eastern Pacific Ocean. And what makes it relevant for us here is that while the phenomena takes place there, the impacts are actually very profound and felt across the United States and various regions here. Why does it matter? Why does something that happens in the Pacific Ocean make a difference here? Well, every day, corporations, our federal government, individuals make important decisions on where they build infrastructure, on where they might locate and create supply chains to keep their businesses going, where they might make investments. And those investments are often made predicated on what we believe to be the future types of weather impacts that will be in different regions. This is something we do very naturally. We look to the past to figure out what the future is doing. But what if the past is not a good indicator of the future? What if a better indicator of the future is variability in something like El Niño? Then the impacts of those decisions can actually have huge financial implications. And the more we know about the changes we expect to see on parts of our planet, the better we can be as a society in preparing ourselves to make better decisions around how we allocate those resources over time scales from months out to decades. To quote Janet Yellen last year, the chair of the Federal Reserve, in some cases when we're not making good decisions about what's in the future, weather and climate can become a headwind on our economy. I'm delighted to be joined by three of the world's experts on El Niño, and they're going to come up here, and each of them is going to spend about 10 minutes sharing some of their thoughts and observations and some amazing diagrams. And we have left the scheduling so that when they are done, there'll be about 30 minutes for all of you, having digested your lunch, to raise your hands and ask a lot of questions that are on your mind about how El Niño may affect you or your district or your organization. I'm joined here by Jan Null. Jan is a lecturer in the Department of Meteorology and Climate Science at San Jose State University. In addition to that, he's a certified consulting meteorologist for the Golden Gate Weather Services based in Saratoga, California, and he's a former lead forecaster for the National Weather Service out of San Francisco, California. And he's going to give you an overview of the El Niño phenomena and some insights as to what we are seeing right now in terms of how El Niño is positioning itself in the Pacific going forward. After him, we'll hear from Dr. John Nielsen-GAMMON. He's the Regents Professor of Atmospheric Sciences at Texas A&M University, and he also serves in a really interesting position as the climatologist for the state of Texas. He's going to talk about some of the impacts, not just in Texas, but elsewhere, of strong and moderate El Nino events and how that impacts people, how it impacts our economy, and how it impacts our way of life. And lastly, we're going to hear from Dr. Clara Desser. She is a senior scientist and head of the climate analysis section within the Climate and Global Dynamics Division at the National Center for Atmospheric Research. And she's going to clue you in on some of the interesting and exciting current research that's going on behind the El Nino phenomena and what our capacity might be going forward to come up with better and better forecasts that we can use. I'd ask that you hold your questions unless they just happen to do with clarification, which is great, then throw up your hand. But once they're all done, we should have time for you to really dig in. So thanks so much for being here, and I'm going to turn it over to Jan.
Thank you very much, Dr. Bogdan. It's a pleasure to be here. Good afternoon, ladies and gentlemen. As Tom said, we're going to talk a little bit about El Nino. And you may have heard some of the media frenzy about some of the predictions early in the summer about what might happen. This actually is a cartoon that came out prior to the El Nino in 1997. So this is not a very new phenomenon. But there are a lot of misconceptions, and hopefully we can dispel some of these, put a lot of this into a perspective that you're able to use in your districts. El Nino never comes to California. It actually never comes to the United States. It stays in the tropical Pacific. It's a phenomenon of the ocean. It's not necessarily going to mean drought relief. I saw headlines in California papers in the fall. El Nino's coming, drought's over. No, I think there's a lot of controversy right there. It doesn't necessarily mean big waves or flooding. So let's talk about normally what happens in the Pacific Ocean. So that large red area on the left-hand side of the screen is where the trade winds push the warmest water at the top of the Pacific Ocean. For reference, on the right-hand side is the coast of South America. The center line is the equator, and then Indonesia is on the left-hand side. The little dotted lines there with the arrows is the Walker circulation. This is the normal situation. During an El Nino year, that warm water shifts more into the central or the eastern Pacific. That changes where the convection is, it changes where the Walker circulation is, it changes the trajectory of the jet streams. Though it's not a topic today, the counterpart for El Nino is La Niña. So this is when actually the trade winds and the circulation pattern is stronger than normal, pushing the warmest water even farther into the Indonesia area. And again, this changes the Walker circulation. It changes the patterns not only in the Pacific, across North America, in different parts of the world. During a typical El Nino, this would be the sort of storm track and weather patterns that we would see. We'd see an enhanced jet stream across the southern part of the United States, wetter than normal weather in the southern tier, dry and warm in the northwest, and dry primarily in the eastern states. Notice that term typical, though. We'll see in a few moments that the way we get these typical events, that we average together a large range of differing El Ninos. All El Ninos are not the same. As I said, the impacts are not just in the United States. You can see the enhanced warming over the Indonesia area, the increased precipitation in the tropical Pacific, and other impacts as we go on around different parts of the world. So even though it's a phenomenon in the tropical Pacific, it has impacts that are indeed global. One of the ways that we measure El Nino is by sampling the sea surface temperatures along the equator. That little yellow box there that says Niño 3.4 is where we measure what's called the Oceanic Niño Index. And when that level, and that is just the sea surface temperature in that box, When that gets more than a ½ degree Celsius or 1 degree Fahrenheit above normal, that's the lowest threshold for a weak El Nino event. When it's above a whole degree Celsius, it's a moderate event. 1.5, it's a strong El Nino event. Here are the, for about the last 64 years, the El Nino events, those spikes going up to the north that are dated. So everything above the line that says weak over there on the right, those would be ones that get classified as a weak El Nino event. And some of the past events, and the memorable ones are the ones that we see that are extending up near the top of the chart. The 1972s, 82, 1997 were all very strong events. Those impacts were significantly stronger. And these are the 22 years that there have been El Niños categorized as our weak, moderate, and strong events going back to 1950. And so there's pretty even spread of the weak and moderate, and just a few less in the way of strong events. So we go, okay, well, now we have all the El Niños. What does it mean? Well, and if we average them all together, so we all take all 22 events and we look at the average amount of rainfall. So this chart shows the precipitation anomaly, how much above or below normal it is. So the greens and the blue colors are above normal, and the yellows and the reds are below normal precipitation amounts across the United States. So if we look at all the El Niños together, you notice this looks a lot like that typical storm track pattern that I showed. So we have above normal precipitation in Southern California, across the southern tier of states, and on into Florida. Drier than normal up in Idaho and on in the Pacific Northwest. But how about if let's dissect it a little bit further. Let's look at just the weak El Niños. All of a sudden, it's a very different picture. Now we have below normal rainfall for most of the West Coast, a good portion of the Mississippi Valley and Tennessee valleys, and kind of near normal conditions for the rest of the country. So this is taking all 8 weak El Niños combined together. Moderate El Niños, the picture changes again. So the flavor of El Nino is very important. Is it weak, moderate, or strong? So we see that a little bit more of that signature that we first saw, that above normal pattern across the southern tier of states, drier in the Pacific Northwest, wetter than normal on the Atlantic seaboard. So 1994-95 winter, and all these charts are based upon looking at the precipitation in the winter months. So beginning in the late summer and going on through the next spring. So 1994-95, well above some record flooding in California, lots of precipitation throughout the West. We also look at 1986 and 87, and I'm sorry, 1986, 87, and look at, that was also a moderate El Nino event. Certainly a bipolar sort of event, a very broad range of conditions, a total flip-flop. So even within categories, there's lots of other stuff going on. That's what you'll be hearing about from a couple of the other speakers, is there's this whole alphabet soup of other indices that we're looking at. Things like PDO, Pacific Decadal Oscillation, and Madden-Julian Oscillation. All of those impact what is going on. El Nino is not the only player in the game. It's one of the strongest types of climate impacts. But just like in a athletic event, you might have a superstar who dominates the game usually, but some days some people will come off the bench and make a difference. So there are other times when these other players get into the act. Finally, looking at the strong El Nino events. Much more significant signature for above normal rainfall across California for sure, and all the way across the southern half of the United States, and even up into the portions of the upper plains and the Midwest. So where are we right now? So that sort of orange blob to the west of the coast of South America along the equator there. That's in that Niño 3.4 region. And that's where we're starting to see above normal sea surface temperatures. And we're also not only at the surface, so not only the sea surface temperatures, but the subsurface temperatures. So this would be like looking at a profile from down in the ocean, the top of the ocean, at the top of the screen. You can see that warmer than normal water moving its way on up into the upper portions of the ocean and beginning to have some of those impacts that we have been talking about. Right now, the forecast that we're looking at, and this is made up of a number of forecasts, but I've put in the average conditions from all the various models here, and that dark black line shows us right sort of straddling that threshold that's between the non-event and the weak El Nino event. The last 2 months in the Oceanic Niño Index have been 0.5 and 0.7, so we're just getting into the category. Now, that's measuring sea surface temperatures, and most of the time that's enough. But it seems that the atmosphere didn't get the memo about it's an El Nino year, so there are some elements that are lacking in how the atmosphere is responding. So we're not really seeing all the impacts that we might see, again, with that typical event. But again, that typical has a large array of different solutions. And finally, just a note to focus back in on my specialty on California. If we look at the top 10 flooding events going back to 1950, and you'll see that only 4 of those were related to El Nino years. 4 of those were neutral years when it wasn't either El Nino or La Nina, and then the final 2 were during La Nina years. So lots of variation, lots of areas that we want to look at and to research. But by this sort of background, it gives some context for what we're going to be hearing from Dr. John Nielsen-GAMMON next. Thank you very much.
Thank you, Jan. He's got his contact information up here. I'll give you a second to jot that down if you want to, and mine will be on the next slide. We've got to focus on some aspects of El Nino's impacts and also El Nino predictions and some other things that go into seasonal prediction as well. As you heard from Jan's slides, they were focusing on the wintertime, and that's when El Nino has the biggest impact on day-to-day weather within the United States. The way that works is basically in the wintertime, the jet stream is far enough south across the Pacific that what's going on in the tropics is able to influence the position and intensity of the jet stream. In the summertime, the jet stream moves farther north, and El Nino's impacts are more felt in the tropics and in the southern hemisphere. And in addition to rainfall, because the whole jet stream pattern is affected, we also have an influence on temperatures during the cool time of the year. With an El Nino, we tend to be cool across the southern United States and unusually warm across the northern United States. Well, warm in a relative sense. It's never warm in the wintertime in North Dakota. But with the La Nina, it's just the opposite sort of pattern. It tends to be warmer in the south and normal and cooler in the north. And so the impacts from El Nino come from basically the consequences of temperature and rainfall, which are the main aspects of weather. I want to highlight some recent research that looks at some of the implications of El Nino. For example, it affects groundwater levels in the southeast U.S., which is important for aquifer water supply levels. That research came out of Auburn University. Impacts soil temperatures and soil moisture, and so the optimal time for planting peanuts changes by 2 weeks in one direction or another, depending on whether you have an El Nino or a La Nina. Wildfires in Florida are very strongly affected by El Nino and La Nina. This next graph here shows the overall risk of wildfires, and the red bars are La Nina, which show very high risk during the late winter and spring. Whereas with El Nino, the risk goes down to 0 during the spring because it's all nicely wet and damp. And then the risk with El Nino climbs during the summer because you have the consequences of this nice wet, damp weather, which all the foliage grows and then dries out in the summer and is available to burn during the summer months. Probably the biggest impact we deal with in Texas and much of the South is with respect to drought. This is showing the change in drought frequency with El Nino. The blue indicates the likelihood of drought on an annual timescale is less than normal. And in that sense, El Nino is usually good news in terms of drought, although it's changing the probability of drought. It's not absolutely eliminating the possibility of it. And conversely, with La Nina, the probability of drought is enhanced significantly, especially from Southern California across the southern United States and into the Great Plains. So we talk about El Nino and La Nina. Jan also mentioned a couple other things going on, which go by the name of Pacific Decadal Oscillation and Atlantic Multidecadal Oscillation. You'll often hear those by their acronyms, PDO and AMO. They're both longer-term variations. We're showing time series here over the course of the past century, and they tend to be in one particular phase for a few decades and then a different phase. And these things affect our weather in different ways. With the PDO, it's sort of like a longer-term version of El Nino. So when it's positive, you have the same sorts of effects. This is the likelihood of drought during the positive PDO, and it's reduced just like it is with El Nino. Now with the AMO, that's more prominent in affecting our weather during the summer and fall when weather systems are coming from the Atlantic Ocean in the United States. And the brown colors indicate where they tend to have drier conditions than normal when the AMO is positive. In other words, a warm North Atlantic Ocean tends to mean drier weather in the United States. One way to think of that is the thunderstorms go where the water's warm, and so they get more thunderstorms over water, less thunderstorms over land. Now, the reason I'm able to talk about this cause and effect relationship is because not just from looking at the observations, which gives us the statistics and the correlations, but they don't show cause and effect so much, but we confirm the mechanisms through models. I'm talking about the same weather prediction models we use to make forecasts a day or a week in advance. Basically, if you plug in this pattern of sea surface temperatures associated with El Nino and run a forecasting model over an entire season and do it several times and look at the average conditions, you find the average under those circumstances is different from the average with normal sea surface temperatures. And no matter which model you use, you get the same basic pattern with wetter than normal conditions across the southern U.S., which is also what our century-long period of observations tells us goes on. So we've got agreement with the models, and the models let us understand what's going on, and in principle, let us forecast what's going to happen in the future. Right now in Texas, we've been looking forward to El Nino as a possibility of improving drought conditions. Right now, reservoir levels in the state are pretty good in eastern Texas, with the blue colors showing close to capacity, whereas in West Texas, they're quite a bit lower, in some cases very low. Here's the total overall state reservoir storage capacity with the black line and actual storage with the shading. You can see we're down about 35% from where our total capacity is right now. And we've been that way since about 2011 when our drought started. And here's a particular reservoir, Palo Pinto, which is in north central Texas. It's the main water supply for one or two counties in that region, and it's down to about 7%. So cities in that area are scrambling to put in connections to other water supplies or dig wells to aquifers to be able to have resiliency in the case of possibility of the water source from this reservoir drying up. We've gone over the past few years from a statewide drought to actually more of a regional drought. I mentioned north central Texas. The hill country, the region around San Antonio is also still in severe 2 exceptional drought. So it's been now 4 years of drought and counting within Texas. And this is a product that we produce within Texas A&M that looks at drought on a very fine scale. You can see conditions can change quite a bit from county to county based upon whatever rainfall happens to occur. Some places get lucky, some places don't. Something like El Nino and La Nina give you an indication of what's going to happen over a multi-state area. But whatever happens locally also depends quite a bit on the weather. This product, by the way, was funded by the USDA as well as the National Oceanic and Atmospheric Administration. And lastly, talking about seasonal forecasting, here's an example of the relationship between the El Nino index on the vertical axis and wintertime rainfall in central Texas. Each of those dots is a different year, starting back in 1895. And you can see that if you try to fit a slope line to this, it would be a diagonal line going upward toward the right. That's how you'd compute the correlation. But in terms of forecasting and understanding what's going to happen, if you know it's going to be an El Nino, moderate or strong, this is what's happened in the past with those circumstances. And the occurrences are clustered around, say, 6 to 12 inches of rainfall if you look along the bottom axis, although it can be very dry or it can be exceptionally wet. If you know it's going to be a La Nina, the points are clustered around a different part of the diagram, say 2 to 7 inches, although again, you can have above normal rainfall with a La Nina just like you can have below normal with an El Nino. Basically, if you know what's going to happen with the ocean, you understand how the climate is going to be changing. You don't know what's going to happen for the weather in any individual year, but the expected weather, the center of that cluster of points, moves from year to year. We're never going to be able to say exactly how much rain will occur on a seasonal basis, but we'll be able to say how the envelope changes, and we can predict El Nino and La Nina. So I'll leave you with my summary here and turn it over to Clara.
Well, thanks for coming out on your lunch hour. It's really a pleasure to be here. I'll continue our conversation here to highlight some current issues in El Nino research, just very broad view here, how our scientific understanding has developed over the years, our predictive skill, and then new exciting directions in El Nino research. So we come to our understanding through three different prongs here. Observations, that's the heart of the beginnings of understanding El Nino. We have some elegant theories with which to understand the physical processes of El Nino. And then we also use our global climate models to model and understand and predict El Nino. So the first thing to say is El Nino is a phenomenon of the coupled ocean-atmosphere system in the tropical Pacific Ocean. It is generated spontaneously. It does not need any external kick or forcing to generate it. So it is something that occurs in our climate system, and it has existed, as far as we can tell, for centuries, if not millennia. We have records in fossil corals, tropical glaciers, and the like, and they tell us that this phenomenon has been occurring naturally for a very long time. So first, observing El Nino, this is at the heart of providing our description, and I would say a cornerstone that's really enhanced our understanding is to have measurements of the water column throughout the tropical Pacific Ocean. We have a set of moored buoys. I helped to deploy some of these buoys when I was a graduate student in the late 1980s, and I'm very proud of doing that. It's a huge effort. These buoys are anchored to the seafloor. This is an enormous task, but they provide us the crucial information of ocean currents, temperatures, saltiness, all the way down through the water column. And then more recently, we have these Argo floats, so-called, and they are autonomous floats that just go up and down in the top 2 kilometers of the ocean, and they're beginning to provide a wealth of data. These are crucial measurements for monitoring and understanding El Nino. And then, of course, we have our very nice global view from satellites, and that provides, again, key information, but it's more surface-based information on the height of sea level, cloudiness, rainfall, and wind patterns. But again, it's these floats and buoys that provide the information about the heat in the ocean, which is a crucial part of El Nino. So I'd say we've boiled down our understanding of the physics of El Nino to a paradigm that we call the delayed oscillator. It's sort of like a pendulum, and I'll show you that more in the next slide. But basically, you can think of the ocean and the atmosphere as influencing each other, and they can, that interaction can amplify and produce a strong El Nino event because the wind is sensitive to the ocean temperature, which is in turn driven by ocean currents, which are themselves forced by the wind. So it's like a loop. And then we have also feedbacks that tend to diminish the oscillation. And the important part here is that the ocean memory, the heat in the ocean, provides this memory that allows the system to oscillate between states. So as I said, it's useful to think of a pendulum. And this is one that goes between the El Nino, the warm state, and the cold state, La Nina. And what brings it into its swings is really the heat in the ocean. In the equatorial Pacific Ocean, when that recharges, that primes the system to produce an El Nino event, and then it takes some years to discharge that heat, and then we will get La Nina conditions. So on the face of it, it looks very simple, that it should be a very regular phenomenon, and what's the difficulty with prediction? But this pendulum does not sustain itself. And in fact, you really need to have some external push or kick on the pendulum to set it in motion. And there are processes that then damp the pendulum so that it stops swinging. So the fact that you need to push it is at the heart of what causes El Nino to be irregular. And that's what makes prediction so difficult. So this is a graph that gets at the heart of this pendulum mechanism for El Nino. And the red curve here, starting in the around 1980 from the measurements from the buoys that I showed you a moment ago, that red curve shows you how much heat is stored in the ocean, in the equatorial Pacific Ocean, in the last 30 years. The blue curve is our index of El Nino that our previous speakers have shown us of the sea surface temperature anomalies in the central equatorial Pacific. And you can see that for all El Nino events in this 30-year record, all of the El Nino events have been preceded by a buildup of the heat content in the ocean. But the time it takes to actually bring the system to an El Nino event varies. And so I've circled in green here during the late 1980s where we had the red curve went above normal and the system was primed for El Nino. And in fact, it took a few years for that blue curve to catch up. I think we're in a similar situation now. And you can see that heat content is ready to go, but the surface conditions that we call El Nino have not as yet really taken place. So again, predicting El Nino, I mentioned that the pendulum needs a kick. There are various ways that the atmosphere and the ocean can set that pendulum swinging. One of the primary ways are what we call the westerly wind bursts, which are winds that are just east of Australia, east of Indonesia. And they can oscillate, they can vary, and whenever you get a strong burst of westerly winds, that sends off a wave in the ocean that then proceeds eastward. This diagram is showing you as time progresses downward, and we're looking at the heat content across the Pacific Ocean. I've marked here when the wind bursts occurred, and then you can see that ocean heat content just progressing very, in a simple fashion, eastward across the basin. So that is really what gives us our predictability. If we know that there's been a change in the winds near Australia, several months later, that will produce this enhanced warming of the upper ocean, and that really provides us the short-term predictability. But the difficulty is, of course, the long-term predictability. A year, 2 years out, can we forecast when El Nino will occur? And there are just physical reasons why that predictability is limited. And one is that we know there's a lot of day-to-day weather variability, and that is not predictable. It's chaotic, it's random, and so much of our predictability will be limited by this random. So finally, I'll come to the modeling of El Nino. Modeling means, in this context, we bring to bear the leading world experts on the physical understanding of the oceans and the atmosphere, and we code this up into our climate models, into our computer models of climate, and we have a lot of complex interactions. You don't need to look at the details just to get a sense of the real complexity of our climate system. And here at the National Center for Atmospheric Research, where I work, we have one of the world-class models built by university partners and also by the NCAR staff. We're up to our 5th generation of the climate model, and I've studied every one, and I would say that with our increased complexity of this model, we also have gotten improved fidelity of our climate system. And let me show you one result. This model produces on its own very realistic sequences of El Nino and La Nina events. So the top curve here is showing you we can run our computer models for as long as we have computer time to do so. And this is a 200-year segment in the upper curve of this Niño index that our previous speakers have shown us, the Central Pacific sea surface temperature anomalies. And this model, without specifying anything outside of the model, it generates spontaneously these excursions of the El Nino index. And like the observations, for which we only have about 100 years of data, the model shows realistic behavior that is irregular, and irregular El Nino and La Nina behavior. And I'll just highlight here in green some periods from the model simulation, maybe 20, 30 years long, in which El Nino does seem to be like a pendulum. It looks pretty regular. And then there are other periods where there is less regularity and maybe more time between events. And again, this is very similar to the observed climate system, this irregular behavior. And the physics of this oscillation in the model does appear to really be realistic, and it does fit this pendulum paradigm. So I'll close with new directions in El Nino research. First, I mentioned that this importance of understanding the different ways that the system can be triggered into an event. It's not enough to just know how much heat is being stored in the equatorial Pacific Ocean. That's a necessary condition, but that doesn't mean that it's followed directly by El Nino. It has to be triggered in some fashion, so it's very important to understand the different ways that triggering can happen. One thing I did not highlight for you, but La Nina events, the cold phase, if you will, they have a propensity to last about twice as long as the El Nino events. And they have very important climate impacts, as we've seen from the previous speakers. So again, maybe we can capitalize on predictability of La Nina events. If we know a La Nina event is in motion, these generally are more long-lived than El Nino. Finally, each event does have unique characteristics, trying to understand why that is the case. And then finally, pressing issue is how will the global impacts, climate impacts of El Nino change as our climate changes? And with that, I think I'll turn it over to Dr. Bogdan. Thank you.
Thank you all for a very interesting and I think very comprehensible tour through what we view as an incredibly fascinating behavior that takes place in our ocean, our atmosphere. And I think you can all see very clearly why the impacts of understanding this better, being able to make forecasts that go out 1 year, 2 years, maybe 10 years of the likelihood of El Nino versus La Nina, can have tremendous impacts on various sectors of our economy that really depend on things like water and temperature conditions. So great job by this group. And now it's your turn to ask any questions. Phil Bai has a microphone there. We'd ask that if you have a question, you stand up and say who you are, and then go ahead and give us your question. And our panel will be delighted to do their very best to answer them. So the floor is yours.
I was wondering if you could elaborate a little bit more on the need for ocean and coastal observations. You mentioned the buoys and the Argo floats. Is that sufficient? What about the nearshore area? Would that help your modeling capabilities?
Maybe we can both answer this question, but it really is knowledge of the vertical structure, the profiles of temperature and currents that allows us to monitor the El Nino system and this buildup of heat. And we need to make sure that these observing systems are maintained. Otherwise, we will really be taken by surprise in terms of when El Nino develops.
Hi, I'm Shri Mishra, also a AAAS Science and Technology Fellow. So I've heard a lot about like how we are actually losing data points in the ocean because there's not enough funding to support the buoys, and those observations are going away. Is there anything in the recent, like I think I heard this 2 years ago, has anything been done to improve this situation?
That there is now a new proposal to sort of do a follow-on to the buoy program. So that the buoys that I mentioned were part of the, it was a bilateral Japanese-US effort over a 20-year period. It was called the Tropical Ocean Global Atmosphere Tethered Atmosphere Ocean Array. And we just finished the 20th anniversary of having all of the buoys deployed, some 70+ buoys. And now they are aging and funding is lacking for maintaining them. So the community is putting together a follow-up program. I apologize, I'm not up to date on the status of that.
Hi, I'm Emily Trinacosta with NOAA Fisheries. And my question is, because El Nino events are so dependent on ocean heat content, is any work being done, or are there any even predictions already of what global ocean warming might do to the occurrence or the impacts of El Nino events?
Yeah, that's a very active area of research, the possible impact of global warming and El Nino. You heard there's a complex interaction between the wind patterns and the depth of the warm water in the ocean and so forth. Presently, we know that some of the things in the ocean atmosphere system are going to change in the direction to favor El Ninos. Others would change in the direction to favor La Nina. And so, unfortunately, the answer is not that simple to come by. And the model simulations that Clara showed are really cutting edge, that we now finally have a model that can simulate El Nino nowadays realistically, and we can start to answer that question. But that's a lot of work is going into that right now.
Maybe I can just add that it's puzzling in our climate models, and this is, I would say, ubiquitous across the models, that El Nino does not appear to be very sensitive to the gradual warming of the oceans in terms of how strong it is, in terms of its amplitude. We're still trying to understand why that is the result. But the impacts of El Nino are being shown in the models to actually become more severe. And that's because as the ocean warms, it evaporates more moisture into the atmosphere, and you'll get stronger thunderstorms and the like, and that actually will fuel stronger global climate impacts in general. So even though El Nino itself may not change in severity, the impacts very well may.
This is Pete Folger with the Congressional Research Service. The California drought that's persisted for 3 years, some people have attributed to this high pressure ridge that sort of parked itself in the Northeast Pacific, which apparently has disappeared. What do we know about the relationship between that ridge, which seems to be one of the primary factors for the drought, and what you're talking about, El Nino and changes in the ocean temperature and the winds and things like that? Is there a predictable relationship there for future droughts?
There really is not. The pattern we've had the last 3 years with that ridge along the west coast, that has been during years when there has not been an El Nino. It broke down significantly in December with some near record rainfall in the state. But now that once we got past Christmas, many areas of the state have not seen any rain. That ridge is back. And so that seems to be an independent feature of it being an El Nino or even a developing El Nino.
Hi, I'm Kristen Lewis. I'm also a AAAS Science and Technology Policy Fellow at NASA's Earth Science Division. In following the prediction of El Nino, a very related question, we know that it's strongly correlated with the heat content, but needs this kick. So do we have any ways of predicting this kick, the uptick in the wind speeds? And furthermore, what observations do you think are more necessary to improve your predictions?
The kick is coming mainly from the atmosphere, and so we've got atmospheric timescales. If it's for example a cold air outbreak from Asia, you can predict things like that a week or two in advance. If it's something associated with the Meta and Julian oscillation, which is mainly a wave of tropical convection moving across, you may be able to predict that 15 to 20 days in advance if you've got a model that simulates it properly. But beyond that, it really is going to be a random process as far as prediction is concerned. Now, once an El Nino or La Nina is developing, you've got several months timescale for it to go through its oscillation process. In forecasting El Nino, in fact, we refer to the spring where those kicks tend to take place as a predictability barrier. Good luck in February saying what's going to happen in May because you don't know how the system is going to be forced. But once you make it into the summer, it's whatever's kicked it is basically died down and it's on its own from that point on.
Thank you all very, very much for coming out and staying with us all the way to the end. Our speakers are going to stick around if you have some questions you want to share with them. We look forward to seeing you later in the year when we'll be talking about hurricanes as we get further into that season. Let's one more time thank our speakers for a wonderful job.